So we all know that concurrency is hard. I mean, I'm not the first one to make this statement in the room today, right? But it's even harder with relaxed memory models, right? So under normal concurrency, you have all sorts of non-determinism and interleaving. But under, for example, a C11 memory model, right, you can get behaviors which are not possible under sequential consistency, right? So C11 memory model is explained, I mean, using this so-called execution graphs, which are over low-level memory events, right? And you have all sorts of relations over these events and so on, right? So we'll go into some details about the C11 memory model later on. But for now, what you need to take away is that reasoning about concurrent programs under C11 memory model is hard. Now, one way to kind of simplify programming under multi-threaded programs, right, is to use the so-called concurrent data structure libraries, right? So Folly is a well-known example of a library for C++. So these concurrent data structure libraries, they are specially engineered, they're highly performant, complex implementations, right? And they are lock-free, right? They take care of all possible interleavings, right, that can happen, and give very strong guarantees, right? So they are formally verified to be correct with this gold criteria of linearizability, right? Which means that no matter what interleavings the low-level operations are performed in, at a high level, right? This all the calls to the library, right, will function as if they were atomic, right? So you get this atomicity guarantee. However, this is only under the SC memory model, right? So only if the accesses, the low-level memory accesses, right, they follow SC semantics. But what about under RC11, right? So we want to have such concurrent data structure libraries under relaxed memory models. Now this is a well-known line of work, right? I mean, there are lots of people who have kind of looked at this this problem, right? And one approach has been to develop new implementations, right? And new specification and verification techniques for building this concurrent data structure libraries, right, under relaxed memory models. And there is a long line of work, right? There are many other works as well. But what we sort of propose in this work is that why not use the existing implementations, right, which have already been proven correct under SC, and make judicious use of relaxed accesses in these implementations to make them robust, right? So what do we mean by robustness? So robustness means that every execution of the library under the relaxed memory model should also be possible under SC, right? Which means that if you run the library under a relaxed memory model, it doesn't exhibit any new behavior, right? All its behaviors can be explained by SC semantics, right? So this is robustness. Now, if you can show that a library implementation is robust, that means that all the correctness guarantees that you have verified under SC also carry forward to the relaxed memory models, right? So essentially, you get a strong guarantee of linearizability, right, for free under relaxed memory model, right? So if we can prove that the library implementation is robust. So this is what we try to do in this work, right? So we have developed a fully automated technique to verify robustness of library implementations for the C11 memory model against the most general client. So the most general client can call library operations arbitrary number of times across arbitrary number of threads. And we also define a new notion of robustness called induced subgraph robustness, which is more suitable for libraries. We have compositionality guarantees of libraries for so-called well-fenced executions. So we'll see what that is later. And we have verified a comprehensive portfolio of robust libraries for standard data structures, such as stacks, queues, sets, and locks. Okay. So let's dive into some details now. Okay. So let's try to see what happens when you execute these library implementations under relaxed memory models, right? What can go wrong? Okay. So to illustrate, I have shown a register library, okay, which is linearizable under SC. Right? So this is not this is a dummy example, right? So this is not how you would really implement a register, right? But this kind of illustrates the access patterns, right, in common library implementations, right? So what this register library does is there is a set operation which sets the register value, and to do that it allocates a new node, right? Dynamically allocates a new node and stores the value in this val field of the node, okay? And it also stores that node location in this shared location L, right? So store is the low-level store operation, right? So for now, you can ignore this RLX, right? What does that mean? We will see it later. Okay. And then there is this get operation which reads the location L, gets the value of that node, and then if R is null, it just returns undef, right? Because there has been no set operation. Otherwise, it loads the val field, okay? So this library is linearizable under SC, okay? But what will happen if you run it under relaxed memory model like the C11 memory model? So here is an execution of this library under the C11 model. So there are two threads here. One thread performs a set1 operation and the other thread performs a get operation, right? Now you can see that here the get operation, right? It reads the value of n, okay? So n is the node that was allocated by the set operation. And from the location L, the get operation reads the value of L. But when it dereferences the value field of that node n, it actually sees 0, right? So this particular execution is not possible under SC, but it is possible under C11 memory model. And this is a classical example of violation of message passing, okay? So this is what we call a non-robust behavior, right? Because this behavior is not possible under SC. So under any interleaving, if you read n, right, from the location L, then you have to read 1, right, from n arrow val, right? Because the writes happen in that order, okay? So this particular implementation is not robust. So how do we make it robust, right? So the way to make it robust is to strengthen some relaxed accesses, right? So this is where this RLX annotation comes into the picture, right? So we are going to change this annotation for two accesses. So we are going to make this store, release store, and we are going to make this load and acquire load, okay? So what does that mean? Okay, so again, let's try to run the same execution under the C11 memory model, right? So now, because of the fact that here, right, the write is a release write and the read is an acquire read, it will create what is called an synchronizes with relation, okay? Because the read reads from this write, and the write is a release write, and the read is an acquire read, right? So because of this synchronization with relation, which is part of the C11 memory model, all the writes before the write to L, right, they come in happens before order, right? So which means that this thread, right, this thread which is executing get, it cannot ignore the write to n arrow val, right? So it has to see that write, which means that we get a robust behavior, right? So this is a robust behavior which is also possible under SC, okay? So just by changing the annotations, right, by strengthening some relaxed accesses, we have been able to at least get rid of this particular non-robust behavior. Now the question, of course, is, are all executions of this library robust, right? So when we talk about executions, we consider the most general client, which means arbitrary number of threads, arbitrary number of calls, okay? So this is the problem that we want to tackle, okay? So in order to do that, so I'll just give a short tour, right, of how our verification procedure works. Okay. So the first thing that we do is we have this declarative characterization of SC executions, right? So one way to sort of reason about SC executions is through interleavings, right? But another way to do it is through this low-level memory events, okay? So for now, I have kind of blanked out this annotations, right? So by blanking out these annotations, I mean that this is an SC library, right? I mean, because it's SC, you don't care about the annotations, okay? And this is the same execution that we saw earlier, right? And this is the only execution that's possible, right? So if, for example, here, right, if by reading the location L, you get the value n, then the read of n arrow val has to see 1, right? So this is the only execution possible under SC. And the reason that is the case is because, again, right, there is this reads from edge from the write which writes n to the read which reads n. And because of this RF edge, under SC you get this another relation called HBSC, right? So this happens before of SC. So basically the write to the val field, it comes in HBSC order to this second thread, right, which is executing get. Because it comes under HBSC order, any future reads cannot ignore that write, right? So that's why this read of n arrow val has to read 1, okay? And this is the definition of HBSC, right? So it's the transitive closure of RF and a bunch of other relations, okay? So, this HBSC must be reflexive. Okay. So why have we introduced this HBSC, right? So we can use this HBSC in order to characterize a non-robustness witness under RC11 memory model, right? So a non-robustness witness is basically an SC execution where you have some thread tau, and the next access, let's say in this thread tau is to location L, and the most recent write to L is in HBSC order before tau, but it is not in HB order before tau, right? So it's exactly what happened in this execution, right? So in this particular execution, this write of n arrow val, this was in HBSC order, right? At this point, okay. But if you had relaxed accesses, then this particular write was not in HB order, right? That's why we got a non-robustness witness. Okay. So there are a few other conditions as well, which we can ignore for this talk. Okay. So this is what, this is the characterization, right, that we use to establish a sufficient condition for robustness, right? So we say that there can be a non-robustness witness only if this happens, which means if there is no non-robustness witness, then such a thing should not happen, right? So basically, for every thread tau, if the most recent write to some location L, right, is in HBSC order before tau, then it should also be in HB order before tau, right? So HBSC should imply HB. If that is the case, then the axis, right, cannot show a non-robust behavior. Okay. So we call this condition as this phi SRC of L. Okay. And so what we try to do is for every execution of the library under the most general client, we attempt to establish this phi SRC, but in an inductive fashion, right, because we have unbounded executions. Okay. So let's see how we could inductively verify this phi SRC of L. Okay. So this is the so-called, I mean, this is the robust implementation, right, or what we think is the robust implementation. So we want to inductively verify this phi SRC invariant, right? So when we say inductively, right, we assume some SC execution, right, so which is given by this box, okay, and we assume that this invariant holds for all events inside this box, and suppose we add a new event eta, okay, in thread tau. So now we want to show that if this event eta is in HBSC order, so I consider the most recent write to this location L, so which is this WL. If this write is in HBSC order to eta, then it is also in HB order to eta. This is what we want to show. If we can show this, then we have inductively verified phi SRC, which means we have shown that this library is robust. Okay. So this event eta, right, what are all possibilities, right? So by looking at this register library, you can see that it has load and store accesses, right, read and write accesses to these two locations, right, n arrow val and L. So these are the only possibilities that eta can have. So we exhaustively explore all these possibilities, right, and see that this invariant is maintained. So for example, suppose this eta was this write of n arrow val, okay. Now it is possible that in some other thread there was another write of n arrow val, okay, and the write of L, right, this is in HBSC order and therefore also in HB order to this write of n arrow val. Now, two writes to the same location are in modification order, right? So this MO is the modification order which relates any two writes to the same location. Now we know that this HBSC is defined as the transitive closure of MO, right? So it includes MOs, and therefore this write to L is now going to come in HBSC order to this write of n arrow val. Therefore we should try to show that it also comes in HB order, but there is we cannot show this right here because this MO is not part of HB. Right? So HB only includes SW and SO, it doesn't include MO. So it seems like we may not be able to establish, right, this inductive invariant, but in fact we will be able to do it because you can see that in this library implementation, right, there cannot be two writes to this n arrow val location because every set method, right, is going to dynamically allocates, right, this new node, and no two set methods will be allocated the same node, right? So therefore there will only be a unique write to every n arrow val for every location n, and therefore this execution itself is not possible, right? So we don't need to worry about this execution. Here is another example, right? So suppose we had a read of n arrow val which will have this from read relation to the write of n arrow val, which also induces an HBSC relation. Okay. Now again we may not be able to show, right, that there is an HB relation from the write of L to this write of n arrow val because again FR is not part of HB, okay, But we can invalidate this particular execution as well. And how do we do that? So we see that this read of n arrow val, it can only occur because of this load, which can only occur inside a get, okay? And the get will return the value that was read, okay? Now we know that there is a unique write to this n arrow val, and this read doesn't see that write, which means that it must return some initial value, right, which let's say is 0. So this get operation is going to return 0. But we know that this library is linearizable, right? So the get can only return a value that was set by an earlier set operation. So this is the specification constraint of the library, right? Which is that for every get method which does not return undef, there must be a set method with the same matching argument value. But we can say that there will not be any set which is called with the value 0, right? So this is a constraint that we place, right? That there is no set with the value 0. But this get is still returning 0, right? Which means that this execution is also not possible according to the specification constraint of the library, right? So in this way, right, I mean, I've gone through only a couple of cases, but you can go through all the cases, right, and see that this invariant is actually maintained. Okay. So we have an SMT encoding which takes as input the library implementation, right? And these constraints, right, the access constraint, specification constraint, and we have another constraint called CAS constraint, right? And this SMT encoding checks all possible partial executions, right, and inductively verifies this phi SRC predicate. Okay. Now, what may happen is that this phi SRC may not hold for all locations, right? So here is an example, right? So if you try to establish this phi SRC for the n arrow val location, right? So I have this I have an execution with 2 threads, right, set 1 and set 2. What you can see here is there are 2 writes to the location L, right? So both writes to the location L will be related by the MO order, right? Now this write of n1 arrow val, this is going to come in HBSC order to the right of L, right? But you will not be able to establish an HB order. Right? So in fact, this write of n1 arrow val is in HBSC order, but is not in HB order. So in fact, we cannot prove phi SRC for n1 arrow val. So what we do here is that we introduce a second sufficient condition for establishing robustness, where we say that instead of saying that for every thread tau whose next access is to location L, if the most recent write to L is in HBSC order, then it is also in HB order, right? So the only difference from phi SRC to phi DSTL is that we also worry about the next access, right? So in phi SRC, you don't worry about the next access to the location, but here you do worry about the next access. Okay. And in fact, we can establish this phi DSTL for the register library, right? So again, we have an SMT encoding which checks these two predicates for all locations, right? And if these predicates hold, then we formally prove that the library is robust. Okay. Now, so I'll go through a couple of challenges, right, in applying this robustness criteria for real-world libraries, right? So what may happen is that there may be implementations which may have benign non-robustness, right? So here is an example of a lock-free queue. Now what I want you to notice, right, is that there is this while loop here, and there is this atomic compare exchange, right, which is a CAS statement. So what may happen is these accesses, right, which I have pointed out, they may show non-robustness, but they will only show if the CAS fails, right? So if the CAS succeeds, right, then you will exit out of this while loop, and at that point it is guaranteed that these accesses will be robust. But if the CAS fails, then these accesses may be non-robust, but then they will happen again, right, because this is in a while loop. So essentially the non-robustness of these accesses, it does not matter, right? It doesn't affect the return value, right? Because the return value is only affected by a succeeding CAS. Okay. So what we do is we introduce this new notion of robustness called induced subgraph robustness, which only considers the robustness of accesses whose behavior affects the return value, right? And we essentially do this by making this CAS a blocking CAS. Okay. Okay. So let me just quickly do one more thing, right? Which is I'll just quickly go through this idea of non-compositionality, right? So if you have 2 library implementations which are robust, their composition may not be robust, right? and we can get this classical store buffering behavior. So what I want to point out, right, is that we introduce this SC fences, right, in order to recover robustness, right, and we show that in the paper, right, we show that if you have such a well-fenced execution involving robust libraries, then it is guaranteed to be robust. Okay. So we have implemented our approach and in a tool, and this tool is also available open source. And we have verified a portfolio of robust libraries. So to conclude, this is the main takeaway, right? So we show that concurrent libraries which are linearizable under SC can be safely migrated to relaxed memory models. And robustness is a good correctness criteria for these libraries because it ensures that every relaxed memory behavior is also an SC behavior. So this SC behavior plays a crucial role in discharging the verification conditions for robustness, and in fact, it helps us in fully in getting an automated procedure, right, for verifying robustness. So thank you all, and I'm happy to answer any questions.
We probably will just ask questions after the session because we are on time. So we have the next speaker come in, please. And if you hang around after the talk, if you have any questions, come on to the finish. Thank you. Thank you again.